Hi everyone, I'm Jun. Recently, I read some papers from ICML 2020 and want to share one paper. This paper investigates how to integrate self-supervision into graph convolutional network. I think it's interesting. At first, I will introduce some background. Self-supervision aims to assist the model to learn more transferable representation from unlabeled data while pre-text tasks through pre-training or multitask learning. It is a subset of supervised learning. And here I show a simple example. The first image is the original frame, and the second one, it removes the color, and then it predict the color based on the gray image. So in this task, this image have no label. It uses its own information. Graph Convolutional Networks. And in this paper, the author used two-layer Graph Convolutional Network. The A in the formula, A cap denotes the normalized adjacency matrix, and ReLU is the activation function. X denotes the feature matrix. W0 and W1 are two weights in each layer respectively. The paper does not apply softmax function to the output, but treat it as a part of the loss. The model parameters in graph convolutional network are learned by minimizing the supervised loss calculated between the output and the true label. For label data, F denote the feature extractor, L denote the loss function. And this paper raised three questions for how to integrate self-supervision to graph convolutional network. The first question is how to incorporate self-supervision in graph convolutional network. The paper proposes three schemes to answer this question: pre-training and fine-tuning, self-training, multitask learning. The second question is how to design self-supervision tasks to improve the generalizability. To answer this question, the paper investigates three self-supervision tasks: node feature clustering, graph partitioning, and graph completion. The third question is, does self-supervision boost the robustness? The paper discusses how to use adversarial training to improve the robustness of graph convolutional network. Next, we will discuss more details about the investigations. And for the first question, how to incorporate self-supervision in graph convolutional networks. And the paper proposed three schemes. The first scheme is pre-training and fine-tuning, here denoted as a PNF. According to table 1, the result shows that this scheme has little performance gains on a large dataset per map. The author argued that switching the loss function from pre-training to fine-tuning is the main reason, because shallow model easily lose crucial information after loss function switching. The second scheme is self-training. The paper used M3S as an example. Here I will briefly introduce what is M3S. With both label and unlabeled data, M3S pre-trains a model over a labeled data and then assign the generated pseudo-label to higher confident unlabeled samples. For the next round of the training, M3S includes the pseudo-label into label data and repeat this process in several rounds. According to table 2, M3S gains saturation as label rate grows higher. The author argues that pseudo-labels are assigned based on their proximity to label nodes in embeddings. The third scheme is multitask learning. In this scheme, self-supervision task is regarded as a regularization term in training phase. According to table 1 again, the result indicates that multitask learning outperforms other two schemes. For the second question, the paper proposed three tasks: partitioning, clustering, and completion. This figure presents the overall frameworks for self-supervision on graph convolutional networks. Partitioning is the task that partitions the nodes of a graph into roughly equal subsets such that the number of edge connecting nodes across the subset is minimized. Clustering is easy to understand. You just cluster the nodes into different groups. Graph completion is a regression task. It masks target nodes by removing their features at first, and then aims at recurring or predicting masked node features by fitting to GCN's unmasked node features. The paper examines that different self-supervised tasks could benefit different network architecture on different data sets. In the third question, the paper generalized self-supervision into adversarial training. These formulas are the generalized form of loss function. According to Table 7 and Table 8, it presents adversarial defense performance on two datasets, Cora and Scythia. The result shows that self-supervision improves robustness without requiring larger models or additional data. Clustering is more effective against feature attacks. Partitioning is more effective against the links attacks. Completion boosts robustness for link attack and both on Cora dataset. In conclusion, firstly, the paper demonstrates the effectiveness of incorporating self-supervised learning in graph convolutional network through multitask learning. Secondly, the paper designs three novel self-supervised learning tasks that benefit graph convolutional network generalizability in different cases. Lastly, the paper integrates multitask self-supervision into graph adversarial training and shows their improving robustness of graph convolutional networks against adversarial attacks. Next, I plan to re-implement this paper. I will implement the experiment on a new data set. Also, I will try different adversarial attacks that I already didn't consider. Thank you. Any questions?